Hello. Today's lesson, we shall be learning about the analogy between electrical and mechanical oscillating systems. So when you speak about electrical oscillating system, you know it is an LCR circuit. And you know a mechanical oscillating system is one that oscillates about its mean position. So where is this question of similarity? We'll discuss that. Both have resonance. For example, an inductor and a capacitor, which is a part of the LCR circuit, are said to have resonance when the frequency is matching, but if there's a phase difference, but when there's a matching frequency. Similarly, in a mechanical oscillating system, you say there is resonance when an object's natural frequency is matched by an outside force which also comes into the same frequency. Then you say a resonance occurs, and when resonance occurs, the output is very high. An example of resonance is people playing guitar or veena or any of the string instruments. These strings have their own classic vibrating frequency, and only when this frequency is matched, they give out sound. So you would have also probably done an experiment in the lab with a sonometer wherein you will strike the tuning fork, take it near a string, and these little paper riders will jump when the string vibrates with matching frequency. So we'll be seeing, we will develop an equation for mechanical oscillating system. We'll also develop an equation for electrical oscillating system, and we'll see the similarity between the two equations. When you speak about a mechanical oscillating system, you speak about two kinds of energy, which is the potential energy and the kinetic energy. And this is matched with, the potential energy is matched with the inductance part in an LCR circuit, and the kinetic energy is matched with the capacitance part. Sorry, potential energy is matched with the capacitance part, and the kinetic energy is matched with an inductance part in an LCR circuit. Now, let us go into this very short explanation. I'll go into the screen sharing mode. Yeah, I presume my screen is visible to you. So we shall start with this. So what we shall be discussing today is analogy. Analogy means similarity. Analogy between electrical and mechanical oscillating systems. So what we will do is we'll first start with the mechanical system. We'll develop an equation for it, then go to the electrical system, we'll develop an equation for it, and then we'll see the similarity. So when I'm speaking about a mechanical system, let me just speak about the spring. I have a spring, okay? And this spring can be extended by applying some force. So I'll say I have a mass M which is going to extend the spring. When you speak about a spring, there are two kinds of energy involved in the spring. When the spring is compressed, there's no force acting on it, the spring is compressed, and you say then the spring possesses a potential energy. Then when a force acts on it, let me say I have a mass attached to this, which means this mass is going to make the string move downwards, let us say through a distance y, okay? So here what happens is there is a kinetic energy involved, right? So now I am applying a force by suspending a mass at the end of the spring, and I'm trying to extend that spring. Obviously, when I'm trying to extend that spring, there is an opposing force which is trying to bring back the spring to its original position. When you speak about the opposing force, there are two components in this opposing force. Let us see both these components. The first component is the one that will try to bring back the spring to its original position. It will try to restore the spring to its original position. So you call it a restoring force. Am I right? You call it a restoring force. And this restoring force is proportional to the displacement. That is, suppose you extend the spring to a very long distance, the restoring force is higher. If you extend the spring to a short distance, the restoring force is smaller. So the restoring force is proportional to the displacement y. Or you could say restoring force is equal to ky where K is the restoring constant. So this is one of the forces acting on the spring. Now there is another force acting on the spring that is known as, let us see what this force tries to do. This force just tries to stop the spring, just like a frictional force. It tries to stop the spring. For example, when you're swinging, when you're in a swinging, you stop swinging, automatically you'll come to a stop. So what is happening here? There is also a force which is trying to stop you. Stop. Or you call it what is known as a damping force. This is known as a damping force. So what does this damping force do? Damping force just tries to stop you and is dependent on the velocity of the spring. So damping force is proportional to velocity. Or you could say damping force is equal to sum B into V, where B is the damping constant. Now, you have applied a force on the spring because of which the spring is extending. So this force, you could say force is equal to mass into acceleration. So this force into mass, this force is trying to pull the spring. When this force is trying to pull the spring, these two forces, this restoring force and damping force, are trying to bring back the spring to the original position. So you could say MA, when you apply a force, these two act against the force. So you could say minus BV minus KY. Obviously, the negative signs are brought in because these two forces are opposite to this force. Or you could modify the equation and write it as MA plus BV plus KY is equal to 0, right? Then I just need to tweak this equation a bit. What is V? V is the velocity. So you can write velocity V. But what is V? V is rate of change of displacement. You know that. So you could write, what is displacement here? Displacement is Y. So you could write V is equal to dy by dt. Similarly, you have acceleration is A, right? Sorry, small e. Acceleration is equal to, what is acceleration equal to? D square Y by dt square, because acceleration, you all know, is rate of change of velocity, and velocity is rate of change of displacement. So acceleration is equal to d square Y by dt square. Now let us incorporate this and this in this equation. So our equation gets modified as M, acceleration, d square Y by dt square, plus B, what is velocity? dy by dt plus ky is equal to 0. I will call it equation 1. So we have got a second order differential equation for mechanical oscillations, right? So now let us slowly go into the electrical oscillations part. So what do we have here? I have an LCR circuit, right? So I have L. I have a capacitance here. And I have a resistance connected, right? And I have a current that is flowing through the circuit. So this is L. This is a capacitance C. This is R, and the charge, total amount of charge in this capacitance I'm taking as Q. So we have an equation for LCR circuit, which you could write as Q by C, right? The charge divided by the capacitance plus I into R, okay? Then plus L di by dt is equal to 0. So now I will again rewrite this equation as L di by dt plus IR plus Q by C is equal to 0. Now what is this Q? Q is the total amount of charge. And current is the rate of flow of charges, right? So current is the rate of flow of charges. So you can say I is equal to dq by dt. So how could I modify this equation? L d by dt of dq by dt, right? Which is I. This is di by dt plus r dq by dt plus I'd say 1 by c into q is equal to 0. Or you could again write this as L d square q by dt square plus r dq by dt plus 1 by c into q is equal to 0. This is equation 2. Now let me write equation 1 here. Equation 1 was m d square y by dt square plus b dy by dt plus ky is equal to 0. Am I right? Now you could actually, what you could do is compare 1 and 2. Compare 1 and 2. So what will you get? So now let us take this part. You will have m is equal to n. So the force that is acting on the spring is equated to the inductance. Then you have B equal to R. What was B? B was the damping constant, trying to stop it. And here you also, in an electrical circuit, you know, resistance will try to stop the flow of current. So B is equated to R. And then K is equal to 1 by C. What is K? K is the restoring force, which is equated to 1 by C of the capacitance. So this is an analogy between electrical and mechanical oscillations. In case there are any doubts, please let me know. I'll try to help you out, right? Okay, let me now stop here.